There I am, ready, waiting for you guys to turn up. We're going to do, electromagnetic induction. Oh, sorry, what made you all wiggle. Right, we're going to do electromagnetic induction this morning. And I mean, I personally think that electromagnetism is the hardest bit of all of the A-level physics. Invisible three-dimensional vectors changing with time, causing other invisible things to happen. And because it's so difficult, I've given it its own little section. Usually it's kind of pushed into the electricity and the magnetism bits of the course, obviously, but I've separated it out because I think it's really, really difficult. And it does bear going through a few things in particular. So you can see how the induced potential difference, the EMF that is induced when you move wire through a magnetic field, is linked to the flux linkage, because there's, just like with displacement, velocity, acceleration, those three time graphs that you learn at GCSE, they're linked by differentiation and integration to go up the other way. We've got exactly the same thing with our flux linkage and our induced EMF. One is the derivation of the other, the gradient of the other, and to go the other way you have to integrate, and that's quite difficult, and it's actually not quite straightforward because there's a minus sign in there. And of course, the flux linkage, if you've got a coil rotating in a magnetic field, you end up with a sine wave. So electromagnetic induction includes circular motion, it includes simple harmonic motion, it includes derivation and integration, although you don't actually have to do that. You do have to have those A-level maths ideas so that you can relate flux linkage to induced EMF. And there's a phase difference between the two, which is something that I pointed out to some students that came along to the session last night, which was meant to be on magnetic fields, but we did end up doing a bit on transformers and a bit on electromagnetic induction as a consequence. And what happened was we recognised that there's a phase difference between an oscillating flux linkage signal variation and the oscillating EMF that's produced, where there's that phase difference, and it's actually 90 degrees, or pi over 2, and I can show you that, and it's one of the things that you really need to kind of get your head round so that you can do it. And then, having got your head round all of this oscillating stuff, then they throw in the odd, well, we're going to do electromagnetic induction on something that isn't rotating. We're just going to shove a coil in, and you've got to deal with the fact that it's moving horizontally with time. Horrible. And they love doing this. They love it. Moving a sensor coil in and out of a bar magnet or a solenoid or something. I mean, it's just, you have to deal with what you've got. There's rates involved, which makes it that much more difficult. Anyway, right, so we're going to do electromagnetism. Then we're going to do, well, it was meant to be materials, but we did do a bit of materials with mechanics yesterday. So work, energy and power I want to focus on for the year 12s. Then we're going to do, after lunch, a game plan. And I did it this way round so that the last session of the day, we are going to update your pathway, update your work plan, and let's see if we can, I can answer any final questions that you have. So the last session of the day is a question and answer session, so that you can go away having had all of your questions answered, ideally. That's the plan. So we're going to start with electromagnetism. Right, pop into the chat if there is any particular part of electromagnetism you'd like to go through. I'd quite like to teach this through the medium, if you like, of questions, because I think that it's all very well going through the theory, but what you need to be able to do is answer questions on it. And so you need to be able to see how to relate those bits of theory, rates and things, with the questions that you're asked. Okay, so pop into the chat which bits of electromagnetism you're particularly interested in. I mean, sine waves maybe, or I mean, there was a really horrible question in 2024 where there was a rod that was falling in the Earth's magnetic field, and when it fell one way, it was giving that you had to describe and explain what happened to the induced EMF in the rod, and then if it fell the other way, you had to describe and explain that, and it was all in one question, and it was horrible. I think that we should go through that, and that would help you with not only electromagnetism, but also to help explain and describe electromagnetic effects, because they kind of have a method of their own for you to, because it's key fact consequence obviously still, but it's the key facts that you start with are not always obvious. Anyway, right, okay, so pop into the chat if there's any particular bit of electromagnetism you want to go through, or are you happy? Right, happy if you're happy for me to pick it. Oh, I've got a happy. Oh, Faraday and lenses law, obviously. Okay, yeah. Okay, so we're going to do Faraday and lenses law. Okay, and I am going to um, right. Lenses law is this. Basically, it opposes you. That's it. Lenses law is a statement of conservation of energy, really. Lenses law says that any energy that you get out, whether it's a current or kinetic energy or whatever it is, any energy that you get out is going to be in such a direction as to oppose the motion, the change causing it. So it's going to be opposite. It's not as simple as that. It's just going to oppose it. Basically, Lenz's law is like friction. Whatever is causing, whatever change is causing it, it's going to try and stop it. So it's in the other direction. In an electric motor you've got a spinning coil in a magnetic field. Guess what? You generate an EMF. And I know. So an electric motor, just because you've got a spinning coil in a magnetic field, you generate an EMF. And that EMF is going to be in such a direction as to try to stop the motor. So it's kind of like friction. So there's a maximum speed that you can get an electric motor to go through because there's this EMF being generated that opposes the motion. And the EMF that's generated is called a back EMF in that situation. Now, it's not part of your specification technically, but anybody who realizes that as soon as you've got a coil moving in a magnetic field should go, oh, hang on a minute. When you've got an electric motor where you're using a current to drive a coil, you've got now a coil and moving in a magnetic field. So surely you're going to be generating an EMF. And the answer is yes, you are. And it's going to oppose the motion. Yeah, not good. So yeah, basically it's friction. A Lenz's law is friction. It's sort of yeah, and it just basically try. I mean, it's friction in that the direction of the current also opposes whatever change is causing it. So it's just awkward. Yeah, it goes nah, I'm not doing that. Nah, that's Lenz's law. It's like a nah. Imagine a 2-year-old that's learned to say no. Yeah, that's Lenz's law. Okay, right. So we're going to pick some questions, and I am going to select a few. Where are we? A few electromagnetic questions. Questions by topic. Right, where are we? Ba-ba-ba. Okay, and we're going to do electromagnetic induction. And I'm going to pull this over and share my screen. Maximize that. Okay. I want to do, Right, this question is quite tricky, but let's do one that is a rotating one. Let's start with a more straight. That's a very long question, this one. Let's start with a more straightforward one. Explain lenses law, you see. It's not nice. Okay, let's do this one because it will introduce hopefully all the things that we need introduced. Okay, so we've got coils. As soon as you see coils, you should go, okay, it's Faraday's law, it's Lenz's law, it's electromagnetic induction, really. The coils make magnetic fields. If you've got coils around a Teltron tube, then it might just be electrons going in circles, but there's a good chance it's going to be electromagnetic induction. Okay, so let's do our ninja question reading on this. Figure 1 shows the arrangement for electromagnetic induction. Right, it's sneaked off the bottom. Can I make this a little bit smaller so I can have the question on the page at the same time? Just go down to the bottom. Can you see it's 4 marks? Right, so electromagnetic induction question. It's obviously the topic. Oh, it's rather fat, isn't it? The topic is electromagnetism. Right, and the number of marks for this first question is 4. What's the command word, please? Pop it in the chat. Explain. And the structure of an explain answer, please. Key fact consequence. Well done. Okay, now it's a 4-mark explain. We've got to explain how Lenz's law predicts the direction of the induced current when the switch is opened and again when it's closed. So we have to explain the direction when the switch is opened. I can't spell switch now. Opened. And we have to explain the direction when the switch is closed. Okay, so, and that's where you get your 4. So you've got your key fact 1, consequence 1 for this first set, and then you end up with the same thing for the second set. You can see where the 4 marks are going to be. Okay. So, right now, have we got any numbers? I can't see any numbers. I can see, yeah, a word that indicates numbers. Yes, clockwise. Good. Okay, the switch being open or closed, this is, that's a number, it's 1 or 0, isn't it? It's either on or it's off, and that's quite important. Okay, there's also an arrow here. Can you see that arrow? Which also indicates a direction. So the clockwise and the arrow, and can you see that they've made the coils darker in the foreground and paler in the background? It's almost like it's in a misty lab, right? So that you can see, you can get an idea of the 3-dimensionality of this. And I hope you realise that those 2 coils are actually sort of concentric, and they're on basically as if they were wrapped around a cylinder that's horizontal. I hope you can see that in your mind's eye. Some people do have difficulty in visualising these things. Okay, so we're told, let's do the reading for meaning now. We're told that when the switch is closed, there is a current in the coil in circuit X. So when this one is closed, there's a current going this way and it goes back up that way, round. It's clockwise. Okay, so clockwise from the point of view of somebody at position P. That's an I. I don't know if you can tell. Okay, then it says circuit Y is viewed from position P. Okay, so you are looking at it from that left-hand end. They've done that because they want to make it clear what point of view you should use when you are describing and explaining things later on in the question. Okay. So, now, what is the magnetic field going to look like around this coil? The X, right? It's coming down this way, up this way. What's the magnetic field going to look like? Okay, I think that it will look like, well, it's going to be fairly straight through the middle. And then because it's a solenoid, it's just a very short one, the field lines will go round like this. There'll be one going straight through the middle. These ones will go around like this and like this. Right, oops, let's do that last one again. Take a little bit more care over it. Okay, so now, which way is north? Because either this is north or this is north. Which way is north? The North Pole. Okay. Now, when you look, I don't know if you know this trick, but when you look at a coil from the end, if you look at it from the point of view of P, okay, we've got this going here and this going here, right? I am going to draw on here an S. Can you see the S, where the ends of the S are the arrows that I've just drawn? So from, right, this end is a south pole and the other end is a north pole. So if you looked at it from the other end, it would look like it was going around the other way. And if you looked at it, so this is from P, and if you looked at it, let's go blue. So if you looked at it from, let's make this one Q, right? You look at the X coil from Q, from the point of view of Q, it's going anti-clockwise, okay? Da, 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 da. Okay, so I've just changed the direction of the arrows. Right now, when you do that, what happens is, if you now go across the middle, can you see it's an N? So from Q, we've got a north pole. Da, da, da. Right now, which way does the field lines go? This is outside the thing. They go the way a north pole would feel a force if you could have a single north pole. So the arrows go away from the north, absolutely, and towards the south, okay? Like that. Inside the magnet, in the side, the solenoid, you'll notice it's the other way around. So please, please, please be aware that it's from north to south, outside a solenoid. How would you figure it out without the shortcut? Oh, you'd have to do Fleming's left-hand rule on a wire. It's not simple. Um, right, what's the concept behind? Right, okay, okay. So, what's the concept behind the shortcut? Right, here is my coil. And if I was to cut the coil in half like that and look at it from on top, right, I would end up with wires going, right, the current is going down this side and up this side. So it goes down this side and up this side. Right, so now I'm going to remove this. Right, now you can do, well, let's not do Fleming's left-hand rule. We're going to do the right-hand corkscrew rule. Okay, so any current carrying wire has a magnetic field around it. So put your thumb in the direction of the current. So at the top, it's sticking out of your screen, and at the bottom, it's sticking into your screen, right? So out at the top, and your field is doing this. Right? And at the bottom, it's going the other way because your thumb's going in. So your field is doing that. Right now, you can now draw another field line further out, but remember that magnetic field lines are not allowed to overlap. And so what happens is that the fields of each of those coil turns, they reinforce. So the next field line out looks like this. And it goes this way. And can you see if you draw the next one, also that way in the middle, that way outside, that way in the middle, that way outside. And that's how the field is generated. It's just got to do with the fact that there's a magnetic field for each turn of the coil. And those little magnetic fields for each turn, they reinforce each other. Okay? Does that help, Aditya? Yeah, okay. So even so, if you do this shortcut down in this bottom right-hand corner, it just saves so much time. You haven't got to do all of this and think about what's going on. Okay. As with all these things, it makes it much easier if you can do the shortcut thing. Okay, right. So I'm going to get rid of all of this because I need a little bit of space. Right. So we've got a magnetic field right now. Can you see that the second coil, because we haven't even got to the point where we've got a second coil. The second coil is in the magnetic field of the first one. So the field lines are cut by the wires. Now, when the switch has been on for some time, the magnetic field is established. Is the flux density through the Y coil, this blue one, is the flux density changing? After the switch has been on for some time and the magnetic field is established, is the flux changing? No, it's not. Good. Which means that you only induce an EMF in the Y coil when you switch it on and again when you switch it off. When it's on and it's been on for a while, magnetic field isn't changing, the flux linkage in the Y coil isn't changing, and you get nothing. And when you switch it off, after it's been off for a while, again, no magnetic field, no change in the flux linkage, you get nothing in Y. But when it's switched on and when it's switched off for a short while, as the magnetic field builds, because the current is now flowing, you do get an induced EMF in Y. And as you switch it off, now the magnetic field is going to disappear because the current is going to disappear. And so the magnetic field goes, and it does take time. Only a little bit of time, but it does take time. And while it's changing, remember that the induced EMF is proportional to the rate of change of flux linkage. So while it's changing, the rate of change of flux linkage is not zero, and you get an induced EMF. And you get one that's one way when you switch it on, and one that's the other way when you switch it off. Because the induced EMF is going to try to stop the magnetic field from appearing when you switch it on, and it's going to try to stop the magnetic field from disappearing when you switch it off. because it's awkward and it opposes whatever change you apply to it, right? Okay, and that is Lenz's law. So now what we've got to do is we've got to explain how Lenz's law predicts the direction of this induced current. Okay, so when we first switch X on, the current is increasing, the magnetic field is increasing. So a north pole on the right hand end of the X coil is being made. And what will happen is that there will be an induced EMF in the Y coil, which will be in such a direction as to oppose the North Pole being made at the right-hand end of the X coil. So the Y coil will create a current in the direction that makes a North Pole this end and a South Pole this end of the Y coil. In other words, it's going to try and push that North Pole away from the X coil. Because I mean it's too small, right? So the North Pole of the X is on this side, and the North Pole of the Y is let me make the Y pink, is there to try to go, no, don't come near me. I'm awkward, go away. No, I'm a 2-year-old. No. Right? So the North Pole tries to push away the other North Pole that is forming. And once it's formed, it's like, okay, right, you got away with it. And it does nothing. What happens when you switch the switch off again? Well, now the North Pole's trying to go away. And so what happens is the induced EMF in the Y is going to go, no, come back. And it's going to turn into a South Pole. I know, isn't it weird? But basically, it's because it's like I say, it's friction. It opposes the change causing it. Okay? Does this all make sense? So now what we've got to do is we've got to explain that. So what is the key fact here? Remember, key facts in physics. Equation. Yes, Lenz's law, but also what's Lenz's law attached to? Faraday's law. There we go. There we go. There we go. Right, Aditya has put it in words, but yes. Right, okay. So this is the one, right? There is Lenz's law, that minus sign, right? And it's delta n phi over delta t. Or you could put minus delta n, but phi is BA, isn't it? Over delta T. Right, now, the Lenz's law bit is this minus bit, which says that any EMF induced is going to oppose a change causing it. Okay, so that is also a key fact. But the EMF induced is proportional to the rate of change of flux. So it only is induced when the flux is either being switched on or being switched off. Okay, so you've got to explain both the opposition thing and you've got to explain this the fact that it's only generated, the EMF, when it's changing, when it's being switched on or switched off. You've got to explain both those things. So I've done it in terms of direction of the switch when it's open and the direction of the switch when it's closed, because that is what's written in here. But there's this other double thing, which is you've got to explain the Lenz's law bit where it opposes it, and you've got to explain that the induced EMF is only happening when the flux linkage is changing. So can you see the things that you need to put in here, why it's 4 marks? Okay, so it's not just, right, the direction when it's opened is obviously the opposite of when it's closed. Obviously, I say obviously, it's only because it's a 2-year-old and it just opposes everything, right? Don't, come over here and play with me. No, go away. I don't want you to play with me. It's literally like that, right? But it's I mean, I think it's obvious because I've been doing this for 25 years. But it's like you've got to say that it's the opposite. But then Lenz's law does say that it's the opposite. So can you see the opposite thing? You've got to say with Lenz's law. The opposite thing is Lenz's law, and the generating anything thing. When it's changing. You've got to say that as well. So EMF only when it's changing. When it's changing, right? So you've got to explain both of those in your explain how Lenz's law predicts the direction. Can you see? You've got to predict the direction from your answer. Okay? Right, so how are we going to answer this then? What are we actually going to say? I'm going to clear the drawings on the right hand side. Can anybody tell me what would your first sentence be when you're trying to explain this? Because this is not simple. Explain questions, especially for electromagnetic induction, really difficult. Okay, so that's why I'm spending so much time on this. So we've got explain. What would be your first sentence? Would it be Faraday's law or Lenz's law? I think basically those are the options, aren't they? Okay. So, closing, right, Lackey. You need to be careful with your language, right? So Lackey has written, closing the switch induces a current in wire X, inducing an EMF. Right now, he's used induces twice. Closing the switch doesn't induce a current, it just drives one. A current is induced in Y. You need to be careful about this use of the word induction or induced. Okay, so when you have a hardwired circuit, you close a switch, a current flows. It's not induced, it just flows. It's forced. Right? So you need to be a little bit careful because one of the things that they are checking when you answer questions like this is the wordy ones is your correct use of the keywords, the scientific words, and induction is a scientific word. Okay, so when you close the switch, a current flows in coil X. That would be a good place to start. Okay, so when the switch is closed, closed, a current flows in coil X. Okay. Then what? Yeah. So what does the current do to X? It turns it into an electromagnet. Okay. So making X into an electromagnet with a north pole on the right hand end. Right, you'd write the whole words out, obviously. Right now, right, so now what we've got is we've made X into an electromagnet. Okay, now we remember that we're not explaining Faraday's law, we're explaining Lenz's law and how it predicts the direction of the induced current in Y. Okay, so this changing flux induces an EMF in coil Y. I think that's what you need to do. This changing flux induces an EMF in coil Y. Good, very good, Aditya. Okay, and you've then gone on to say it has a magnitude proportional to the rate of change of flux linkage, which is explaining Faraday's law. Have you been asked to explain Faraday's law? No. So what you've got to do is not explain Faraday's law. You've got to explain how Lenz's law predicts the direction of the induced EMF. Okay, so we've established that there's an induced EMF. Right, now what we've got to do is we've got to explain how Lenz's law predicts the direction of that induced EMF. Can you see? You must answer the question. You've got to do what they've told you to do. So this changing flux induces an EMF in coil Y. Right, now, Lenz's law says, can you see? Lenz's law, this is another key fact, law says, well, what does it say? It says that the direction of the induced EMF, right, says the direction of the induced EMF is going to oppose the North Pole forming by creating a North Pole on the left-hand side of coil Y. I can't fit it in. I've run out of space. On the left-hand side. Yeah, so it's going to oppose the change causing it. Right, I suppose we could do the change causing it. Okay, i.e. the North Pole forming, right? And then by creating a North Pole on the left-hand side, I can't fit it in, side of coil Y. So you can then say that the current in coil Y, when viewed from point P, is going to be, well, which way? So from point P, we want a north pole, this end, and a south, right? So from point P, we want it to look like that, a north pole, which means it's going to be going anti-clockwise. Okay? So you can say that the current induced in Y will be going anti-clockwise when viewed from P. But only for a short while. As soon as the field's established, that current disappears. So if I was to, right, I'm going to clear my drawings. I hope if you wanted to do a screenshot, now would be a good time. And I'm going to clear my drawings because what I want to do is is everybody understanding this? I am getting some yeses. That's good. I've cleared my drawings because I want to point out that when you switch the current on, so let's look at the current in Y. So this is I in Y with time, right? And let's imagine that this is the point when the current is switched on. Okay, and this is the point where it's switched off. Okay, so I'm going to write it down here, off. Right, now, if we say that the current going in the anti-clockwise direction is positive, when the current in X is switched on, we're going to get an anti-clockwise. So this is anti-clockwise current in Y, but only for a little while. Okay, so it's going to, as soon as it's switched on, it's going to go blip. And then nothing will happen until it's switched off. And then it will go blip the other way. Okay, so and I always think, I mean, and of course, I is proportional to V. So V for Y or I for Y would look the same. It happens to be an ammeter they've got in this. Okay. Oh yeah, on the right hand side of, yeah, you're quite right. Yes. Yes. I wasn't careful enough. Yes, well done. Yes, well done, Aditya. I mean, that attention to detail, that shows, well, first of all, you're really paying attention. And secondly, it shows that you really understand what's going on. It can't happen before the cause. It happens afterward. But only for a little while, because as soon as the established magnetic field disappears, the induced EMF just goes as well. So what you've got to say then is what happens when you switch it off. So we did when we switched it on, and then you've got to say the opposite happens when you switch it off. The current induced in Y is going to try to stop the North Pole from disappearing, so it will become a South Pole, so you get a current in the other direction, or something like that. I mean, the exact words are not crucial. Some of the keywords you must use correctly, but the exact words are not crucial. So there will be multiple, or you could say this, or you could say this, or you could say this in the mark scheme for this. And I'm going to, let's go and have a little look at the mark scheme so that you can see the sorts of answers that are okay and that will actually score you marks. So this is question number 4 and it's part A. Oop. No. Question number 4, 2, 3, 4, and it's part 3. There's 4. Gosh, 3 was a long question, wasn't it? Part A. So, right, we've got induced current is such as to oppose the change producing it. That's the definition of Lenz's law. When you switch on, the current increases the flux through Y, and the current is going to oppose. Can you see? It's anti-clockwise to oppose the creation of the flux. And then when you switch it off, the flux through Y due to X decreases so that the current travels clockwise to create the flux to oppose the change causing it. Okay, so 1 mark for Lenz's law statement. Can you see? And 2 for explaining what happens at switch on or switch off adequately, and 1 for completing the argument for the switch on and switch off adequately. So you get 2 for explaining when you switch it on, or if you explain when you switch it off, and you get 1 for explaining that it's the opposite when it goes on to when it goes off. So can you see this is the logic of it. Those 4 marks are, because this was an explain, remember? The key fact is Lenz's law statement, which I don't think you can do with, well, I mean, I like using the equations, and you can't state Lenz's law without Faraday's law, but the Lenz's law bit Can you see? I did caution you from explaining Faraday's law. I'm not explaining that here. So you had to state Lenz's law, and then two for explaining what happens at the switch. So what happens when you switch it on or when you switch it off. So when you switch it on, you have to say that the current, the flux linkage phi, n phi, let's go, goes up, and you induce an EMF, which is in the direction to oppose it. And so you've got to say both of those things. And then you also, so that's one mark, that's one mark, that's one mark. And then the final mark is for explaining that it's the opposite when it's switched off. Because it's trying to stop the magnetic field from disappearing. Okay, so that those can you see the structure of the four marks? That's why they've put them in there, and they've put that in there because they recognize that you're not necessarily going to say exactly that. So they're kind of saying, look, when you're marking this, think about the first mark is for saying some statement of Lenz's law. The second mark is for saying what happens when it's switched on and explaining that. And then you've got to explain why it's the opposite when it's switched off. Okay. And can you see that they've said, look, this is their logic. These are what we expect you to give the marks for. This is what we're expecting them to write, but they might write all sorts of things. And this is the logic. And you've got to have a little look and see what they've written and see if it fits with this logic. Do you understand what I'm trying to say here? So it doesn't, I mean, I thought it would say, or this, or you could say or this, or you could say all this, and there'd be a number of things that you could say that would score you marks here. But that's not how they've chosen to write the mark scheme for this question. They've said, this is the logic of the question, and this is where you give the marks. And we're expecting people to say this, but maybe they won't. This is the logic. If they say something, or words to that effect, kind of thing. Okay. On the right hand side of the line, though, right, as in the off. Right, yep, sorry, I was reading that, but that was a message from a while ago. Right, okay. We spent quite a long time on that, but I do think that that was actually a really helpful and thing to do. Because explaining this sort of thing is quite hard. Right, now, let's move on to this next bit, which is, right, well, what have we got? We've got an earth conductor an earth inductor, get it right, consists of a 500 turn coil. So there it is. Figure 2 and figure 3 show it set up to measure the horizontal component of the Earth's magnetic field. When the coil is rotated, an induced EMF is produced. So how is the coil going to be rotated? I think the coil is, they haven't made it clear, have they? I think the coil is going to be rotated around there. Like that. I think. Yeah, like on the y-axis. Yeah, absolutely. So, so it's going to come toward you like that, and then it's going to, and it'll spin. So there is the axis, and it's spinning like that. Maybe clockwise, maybe anti-clockwise. Doesn't really matter, does it? But anyway, right, okay. So I think that's what's going to happen. And what happens then? I mean, basically, you're using the Earth's magnetic field as your magnet, your permanent magnet, to generate an EMF. It's not going to be a very big EMF, is it? Because the Earth's magnetic field is not very big. Bearing in mind, um, um, you need to know the approximate sizes of things. Does anybody know in Tesla how big the Earth's magnetic field is? Approximately. It's only an order of magnitude thing. 10 to the what? Tesla? 10 to the minus 1? Any advance on 10 to the minus 1? Okay, 5 times 10 to the minus 6 is 10 to the minus 5. Yeah? Yeah, it's about 10 to the minus 5. So, Lucky, you're a little bit small, and yeah, and Angie, you're a little bit big. Yeah, 10 to minus 5. It's not very big. Well, actually, to be fair, 1 Tesla is an enormous magnetic field. It's huge, right? So 10 to the minus 5 is the approximate size of the Earth's magnetic field to an order of magnitude. Okay, so it's not very magnetic. I mean, yeah, I mean, it is in that, right, it's an enormous, I mean, physically huge field. And it does protect us from cosmic rays and to some extent, and cosmic coronal mass ejections and stuff from the sun. And you know that that's true because we get the northern and southern lights where the magnetic field lines concentrated at the poles. We get lots of charged particles hitting our atmosphere, and they glow, make the atmosphere glow, which is the northern and southern lights. And you get way more northern and southern lights when you've got more charged particles hitting. And what that shows you is that the magnetic field, it's called the magnetosphere of the Earth, is protecting us from dangerous radiation, particularly from the sun. So yeah, it's big in one way, and it's not that big in terms of Tesla anyway. Okay, so we are basically using the Earth's magnetic field as a generator. We're deliberately spinning our coil, and we get, look, microvolts out. Microvolts. Okay. Right, and we've got the coil is rotated 1.5 revolutions per second. So the frequency, because that's oscillations divided by seconds time, isn't it, is 1.5. So it's 1.5 hertz. Okay. Right, the mean diameter of the turns of the coil is 35. So D for the coil is 35 centimeters. And we've got this EMF right now. They want you to determine the horizontal flux density, right? It is only the horizontal flux density that is going to be changing. The vertical component is not going to change when you spin the thing, right? So it's only the horizontal one. And they've kind of gone, well, yeah, let's just think about the horizontal one. So let's make it a little bit easier for them. Let's imagine that there is no vertical one. So we're just doing the horizontal component. So that's the bit that actually affects anything. So now, how can we do this? We've got, right, it's 3 marks, okay? So it's a reasonably difficult thing to do. So we've got to get B, okay? We've got to get B. That's what we've got to get is BH, but let's get B. How can we relate that? And it's the command word is determine. What does determine mean? What's the difference between that and calculate? Yeah, we got to use the graph. What do you think we have to use about the graph? Amplitude, good. Okay, so the amplitude is our maximum induced EMF, isn't it? I'm going to call it E0. This is the maximum induced EMF, right? So get your equations out, people. What are the equations which start E0 on your data sheet? Okay, I'm going to write one down. Okay, so we've got E is minus delta n phi over delta t. Okay, but we've got an oscillating thing going on here, haven't we? So there is another one, isn't there? Let me pull up the data sheets. Where are we? Yeah. Right, so if I pull it over there a minute, okay, so we've got, can you see on here, we've got um, E is there. So E is BAN omega sine omega t. What's omega, people? The angular velocity. Right, good. So omega is the angular velocity. Okay, which of course is 2 pi over t or 2 pi f. Oh, look, we've got f. Okay, right now, that is E, not E naught. Oh, epsilon, not epsilon naught. What's the maximum that that equation can take? Yep, it's a maximum when sine of anything, the sine of the angle, is 1, because that's the biggest sine can be. So epsilon naught, it's not on your data sheet, but epsilon naught is BAN omega. And omega is 2 pi f, so it becomes BAN 2 pi f. That is epsilon naught. So there is the equation that we're going to use to work out, and it's only the horizontal component that we're interested in for our horizontal. Right, so now let me get rid of the data sheet again. That's the way. So now we're going to determine our BH. So I'm going to rearrange this bottom right-hand equation, and I am going to use this space here. And I'm going to write BH as the subject of the equation. So it's epsilon naught over the cross-sectional area, the number of turns, and 2 pi f, which is omega. Right, now, we haven't got the area. What have we got? We've got the diameter. So can you see how easy this is if you are confident using the information on your data sheet? Okay, right now, so we've got epsilon naught over, and then the cross-sectional area in terms of the diameter is pi d squared over 4. I'm going to put my 4 on the top. That's my A. I've still got N. I've still got 2 pi F on the bottom. So I've actually got pi squared on the bottom. Let's do a squared and get rid of that one. Okay. And now I can write it down. Right. So I'm going to put my numbers in now. So I've got 4 times my maximum induced EMF is there. I reckon it's 5.6 microvolts, so times 10 to the minus 6. So 5.6 times 10 to the minus 6. That's my maximum, my peak voltage from the middle. It's always measured from the middle, right? Divided by pi squared. D is 35, but it's centimeters. So it's 35 times 10 to the minus 2, and we've got to square it. N was 500 turns. We've got a 2 in there, and we've got F, which is 1.5. Horrible, isn't it? It's not that hard once you've realised that you can use this equation and it's a maximum when that's true. Yeah. Now, OCR doesn't have this equation, right? So they would either have to give you the equation or they would not ask you this question. This is an AQA question, which is why I was looking at the AQA data sheet. But they might ask you something similar. I mean, not okay. So why is the equation in two boxes include sine omega t? Because you only get an EMF induced when it's changing. Right, I'm going to have to do the theory. Right, can somebody actually do this sum on the bottom left-hand side, and we'll do the answer. So, can somebody tell me what this number is, or if I got to do it? See if you can beat me. 4 times 5.66. Okay. I'm using the diameter, but I did divide it by 2. There is like 2 squared on the bottom. Okay, right, so I get 1.24 times 10 to the minus 8. That doesn't sound right. I've got a factor of 3 missing somewhere. A 10 to the 3. Oh, it's just a horizontal component. It might be right. It might be right. I'm going to just quickly go and look at the mark scheme for this. So this was question 4 still, and it was part B. Question 4, part B. Yes, 12.4 nano Tesla. So we were right, because it's just the horizontal component. Right. Right. Now, I have had a question from Jero. Why is there a sine omega t? So I think what I need to do in order to answer that, Jero, I'm going to have to take us back and do a little bit of theory. Okay. So I'm going to stop showing this and pull up a whiteboard. Okay. I'm not going to prove this to you. But if you've got a coil, I mean, it happened to be a round one, but quite often they're drawn as square coils, aren't they? Like this. Between 2 poles of a magnet. Okay, so this is my north pole and this is my south pole, for example. My axis of rotation, I'm going to draw in red. And I'm going to rotate this manually. I'm going to literally turn it with a big fat handle on here. So there is my handle, and I'm going to rotate it. Okay, round and round and round it goes. Okay, are you happy with that, Jero? Good. Right, now, when I rotate it, what happens to the flux linkage that goes through the area of the coil? I can draw a graph of what happens. Okay, so if I start here, it actually starts with the flux linkage through the coil. Starts at 0, doesn't it? Actually, perhaps I should have drawn it vertically. I don't know. But anyway, let's just draw it like this. It doesn't matter. Because it's circular functions, it just shifts everything along a little bit. Okay, so we've got n phi, and it changes, but it changes because it's circular motion. We end up with the flux linkage doing this, isn't it, continuously? Now I'm going to change this. I don't like this because it's just going to confuse you. Right, hang on a minute. I'm going to change it. It is like that. And there is my line of rotation. It's still going round that way. It's very similar. It's just that it's starting there, which means that my flux linkage starts there. And I want it to be a cosine, which is why I made it start there. Okay, so if I were to write an equation of how this is changing with time, I would say that my flux linkage this is a function as a function of time. Can you see? It's BAN. The BA is this. The N is this. But because it's rotating, it's cosine omega t. Right? Omega is the rate of, the angular speed. So, and remember that omega then, because it's the angular speed, is theta over t. It's the angle divided by time, just like linear speed, but for angles, right? Which means that if we want the angle, then we have to rearrange that. We get theta is omega t. So I've put that in there instead of theta. Right, now, Gero, do you do further maths or just maths? Just maths, okay. So are you happy, though, differentiating trig functions? Oh, good. Lovely. Okay, differentiate that with respect to time. So I want, like the EMF is the rate of change of flux linkage. It's actually negative, the rate of change of flux linkage, minus, right? Which means that it's minus D of BAN cos omega t with respect to time. Okay, so we get our EMF is, I'm going to make it a bit smaller so you can see everything all at once. So when we do this, we get BAN, whoops, I'm writing N, I'm saying A, BAN, right? The omega that's in the cosine comes out, omega. The cosine turns into a sine when you differentiate, sine omega t still inside the brackets, right? The minus, because when you differentiate cosine, you get minus sine. The minus means that this ends up being positive. Okay, so it's not a minus sign, it's a sine. Okay, and you end up, I can line up my EMF thing, right? So it's a sine omega t, so it does this. With time. That's where the sine comes from. That's what's written on the AQA datasheet. Does that make sense? Okay. Now, the maximum EMF is then given when sine omega t is 1. And something that I pointed out to my students, the ones that turned up for the regular Zoom session last night, is that you get the maximum EMF when the flux linkage through the coil is 0. And the reason it's that is because that's when it's changing most quickly. It's the gradient of the one above it, isn't it? So the gradient here is 0, so you get 0. The gradient here is large and negative, but it's minus the gradient, so it's large and positive. The gradient here is 0 again, so you get 0. The gradient here is large and positive, so you get large and negative. The gradient here is 0, so you get 0 again. Right, now, you haven't got to be able to differentiate trig functions to do A-level physics. But you do need to be able to do this sort of hand wavy. It's 0, large and positive. It's 0, large and negative. Da 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 da. You do need to be able to do that, and you do need to know that the EMF is the differential. It's the gradient of the flux linkage curve, and the flux linkage is changing with time simply because the thing is rotating. They are circular functions. Sine, cos, and tan are circular functions. You find them in circles. You do know that they're circular functions, do you? Does everybody understand what I mean by circular functions? Please pop in no if you're not quite sure. Okay, nobody's putting a no in. Okay, so because it's rotating round, you're getting the sine wave. It's just one dimension of the circle. And then you get an oscillating signal. So basically it goes up and down, which is like, it's like the x coordinate are only of circular motion. And if you combine it with the y coordinate, right, you end up with things going around in circles. Yeah. So but so simple harmonic motion, this is why you need to have your simple harmonic motion before you can do electromagnetic induction. Right. I hope. Right. So various things to learn, that there are complicated equations that you can apply so long as you know what everything means. You can remember that when sine of anything is a maximum, the biggest it can be is 1. When cosine of anything is a maximum, the biggest it can be is 1. Okay. And which means that you can get your peak EMF. Your peak EMF. And then the next thing they end up doing is making you work out the root mean square voltage, which is the equivalent DC voltage. So all you have to do is follow the equations on your data sheet if you've got them. And I think they're certainly on the AQA one. So here, oh, you can't see that, can you? Because I'm not sharing my screen. So here, this V0 is your induced EMF, right? So that's your maximum, that's your peak voltage. If you divide it by √2, you get VRMS. That's the DC equivalent. So you can do your pink is viol, P is IV type equations, or V equals IR, and you can pretend that it's a DC circuit. That is not. Okay? Okay. Lots and lots and lots to think about there. We have run out of time. I hope that has helped you a bit. It always is difficult doing electromagnetism questions. So if you would like a bit more on electromagnetism, pop into the chat and I will send, I think what I'll do is I'll add some electromagnetism videos into this bit of the Easter course, so that you can just click on some links and get some more teaching on electromagnetism if you need it. Okay, I would recommend that you practice questions. Everybody has access to the turbo tutor. 1 or 2 of you are using it. If you were to try some electromagnetism questions and get a bit sort of stuck or confused, take a picture, pop it into the turbo tutor, the WhatsApp group, and ask for help. Just go, help with question 1.6. One question at a time, please, not a whole paper. Thank you. Right. Okay. We are going to stop for a break. We're going to start again exactly at 11:30 because I'm hoping that the year 12s might join us and we're going to do work, energy, and power. All right.